it's not choose the existing cluster. It's large algorithm to simply the new cluster. As somebody that comes in, this cluster will be multiplied, therefore.
All right. Hi, everyone. We're going to get started now. So, welcome to the last lecture, the last official lecture of cognitive robotics for this semester. This is our last day of lecture, but next week we'll still have class, but class will be held in 32226 in the MERS lab, because we'll be having a dry run for the grand challenge on Monday. So what that means is that you can basically come with whatever state of code you have. We can try and integrate it with the robot, get things working, and so on. Just sort of like an open lab hours sort of thing for class time next Monday. So you should all come to that. Where you can also set up additional time with the robot, with either me or Tiago if you wish. Just send us an email and we're happy to arrange that as well. Alright, so today's lecture will be delivered by Boba Fett in honor of today being Star Wars Day. May the 4th be with you. Well, in all seriousness, today's lecture is given by Pedro Santana. It'll be a very interesting lecture about an algorithm he developed called RAO star, which is an extension in many ways to the LAO star algorithm we talked about last week. To the AO star algorithm that was alluded to last week, but it deals with risk explicitly. So without further ado, I hand it over to you.
Let me just add a few more sentences. Though I have to admit that I am quite scared. So if you look at the theme in the class, right, that we kind of introduced at the beginning of the class the notion of model-based programming, and we introduced the notion of programming on state, and then we spent a fair amount of time also talking about dealing with temporal constraints. So Monday's lecture, you saw kind of how do we add in the issue of uncertainty and risk within temporal constraints. But a lot of what we've done is we've looked at in the case where you're writing programs on state, you're using some form of heuristic forward search planner, right, to generate a set of actions. And that really increases the level of autonomy that you have in the system. So just kind of coming away from the course saying we could program the levels of states if we have very good generative planning capabilities, right, then I think that this is a central takeaway. But you really want the systems to be able to do things which aren't too risky, and that's important to deal with. But even more, the way that we deal with life is that we plan contingencies along the way. So we're very good at thinking of different ways to try to deal with different kinds of failures and then how to come up with the most likely contingencies. But there hasn't been a huge amount of work on that and trying to formalize that process of what's a good enough set of contingencies. So I think what's really nice in Pedro's lecture, the Wrapup lecture, is to talk about how can we generate a set of conditional plans or contingent plans so we can handle the most likely outcomes while still having some guarantees about the things that I've ignored won't kill you with more than an acceptable risk. Okay? So once we see Pedro's friendly smile behind the mask, then we'll start learning about RAO star.
All right, thank you very much. I'm going to remove the helmet, so I just want to say Happy Star Wars Day. It's a great pleasure. Okay. Enough. My nose is too big, it doesn't fit the helmet. It is a problem. Perfect. All right, so good morning, everyone. I'm Pedro. It is my pleasure to give the last lecture in 16412, maybe my last lecture. But anyway, so today, as Professor Williams said, we're going to talk about risk-aware planning. And then today, because education and learning is an active experience, I expect active participation from all of you so that we can go through a lot of these concepts very quickly and then kind of like sear them into your brains. So first of all, let's start with the motivation. And before I tell you the kinds of applications that I have been looking into and people who usually use risk-aware planning for, I would like to hear from you, where do you think risk-aware planning could be useful? You're taking an autonomy class, so you probably have something in mind.
Like planning paths through obstacles, around obstacles.
Perfect. Path planning is a great example. So if you're trying to, chance-constrained path planning, or risk-aware path planning is a great application. And actually, path planning, whenever you have robots involved in any sort of task, path planning or collision avoidance is always some sort of like, if not the main goal, it's one of the most important submachines that you have to run. And I'm going to show you something about it. Anything else that comes to mind?
Reliabilities, what's the probability you're going to fail or miss your deadline?
Exactly. So when you say miss your deadline, so another sort of planning. So planning is basically in every aspect of our lives. And when you have temporal planning, such as, for example, what Andrew presented last lecture, you could also have plans that have a keen, it would have like a keen sensitivity to temporal risk. So if you're trying, for example, to communicate with a satellite, it's going to only be available during some time window. And you have uncertainty in terms of the durations of the tasks that, let's say, a Mars rover has to execute. You might want to generate schedules that are robust to that uncertainty and can guarantee, at least with high certainty, that you'll be able to communicate with the satellite. All right? Cool. So now let me try. So these are actually, so science agents such as, for example, Mars rovers, which we see a lot in the media, but at the same time, you don't have to go all the way to Mars to find challenging scenarios where robots can help us. If you go, for example, in our partnership with Woods Hole, they have these autonomous robotic explorers that go around the world exploring the seafloor. And these environments are way too, because you have such big water columns, it's very hard for you to do remote control of these agents. So they have to be autonomous, but at the same time, they need, if they are not aware or if they don't have a very keen sensitivity to risk, they might actually end up in a risky situation or causing the mission to fail because they didn't take uncertainty into account. Another application, you probably recognize your lovely TA from this picture, one over there. Robotic manufacturing is another domain that could really use risk-aware planning. Because especially when you have humans and robots working together, especially on the robot side, the human is a great source of uncertainty. It is very hard for people in general to try to predict the behaviors of other humans, and especially hard for robots. So being able to fold these notions of risk-aware planning into these applications is an enabling technology to allow humans and robots to work effectively, collaboratively in these manufacturing scenarios. Another interesting domain that I've for my thesis, and then which has real-world application, is power supply restoration, which is basically you have a big urban power supply, and then let's say, for example, that there is a fault that causes a blackout down this feeder. And then the problem is, assume that you can't really observe this fault. The only thing that you can observe is that this circuit breaker opened and threw all these people in the dark. So the question is, so for example, one way to mitigate this problem is you could open this switch here, close this one and reroute power from this feeder, and then you can open this switch here and reroute power from this feeder. And then the question is, could we do that while not having information about the exact location of the faults, and while making sure that the probability of causing further blackouts is small, right? And then this one is hopefully the, so this is actually a recent case where we were using RAO star in a scheduler that Andrew presented in the last lecture to basically solve what we call the resilient space system scenario. So basically what we have here is a Mars rover that has to go around and do exactly what I mentioned before. So it has to go around this map. It performs risk-aware path planning. You're actually going to see it running here. And then what it has to do is it has to plan a set of actions and plan a schedule that will allow it to collect all the things that it must, and then communicate with the satellite during the time windows in which the satellite is available. You can actually see it in these locations. So just to show you that these things actually work. And I'm like, if you guys like video games, you might recognize something. So here, so our star is running here. All right. So what just happened up here is that it generated a sequence of actions by doing so, it took into account the uncertainty in the temporal durations of the task that the robot has to execute, and then generate a schedule that will then, not only it is feasible, but will meet the constraints of being able to communicate with the satellite. And then, this goes on for a long time. And here, for example, the risk-aware path planning that was just mentioned by the gentleman. So this is just to show you that risk-aware planning is a useful tool to have, especially when you're trying to develop these large-scale autonomous systems that have to operate in these uncertain environments and deal with different kinds of uncertainty in their planning process. Right? Okay, so in the lecture today, this is basically our goal. So the question is, can we generate plans that try to optimize performance in terms of we want our agent to perform as well as possible, while you guarantee that these plans are safe, and we allow both the stochastic, the transitions, the state evolution of the system should be stochastic, so there is uncertainty in the state evolution, and also we allow the state to be partially observable. So the state is not directly observable as in an MDP. In this case, we can only rely on sensory information in order to be able to refine our uncertainty about the true state of the system. Right? So we only have 3 topics for today. Hopefully you all feel motivated to learn about what I'm going to start talking right now. Then for the next few 20 slides, I'm just going to make sure that we all understand how to handle belief states, which is an important part of the RAO algorithm. And it's kind of like basic probability, but I just wanted to make sure that everybody understands what I'm talking about. And for example, if you wanted to re-implement this algorithm in the future, you can just go through the slides and re-implement it, and you understand every single step of what is involved. It's actually quite simple. All right, so before we start talking about belief states, every time I think, probability is usually a daunting subject, but every time I think it's hard, I just read this quote by Laplace, and then I feel bad that I think probability is hard, and then I try harder, and then things will happen. All right, so basically, since we're dealing with systems with stochastic transitions and hidden state, we're basically going to be working on the framework of hidden Markov models. I'm not going to give you a thorough introduction. So who is here is familiar with hidden Markov models? Oh, perfect. Well, that's great. I mean, I'm not going to give you a thorough introduction. The only thing that you have to care about is in a hidden Markov model, you have a discrete set of states. You have stochastic transitions between these states. But for example, in an MDP, a Markov decision process, is nothing more than you trying to control a Markov chain. And then in these cases, what you have is you have your beautifully drawn eye. And as the system is performing, so even though you cannot tell sometimes what transition the system is going to take, every time it takes a transition, you can go there and observe. And you can say, well, I don't know what's the next step is going to be, but once it happens, I know exactly where the system landed. In an HMM, unfortunately, we're going to throw this kind of cloud of smoke in front of the states. And now what we're going to have is we can no longer directly observe the state of whatever is going behind the scenes. The only thing that we can observe are sensor measurements, usually noisy, that poke through the cloud of smoke. And of course, that makes the problem significantly harder. But this is basically the framework in which we're going to be working.
Quick background questions. Do you assume finite number of hidden states or infinite number of hidden states?
Let's assume finite, but it plays no role. But I do assume that they are discrete. So here we have, let's say that we have a Markov chain, and by Markov chain I say every state is only dependent on its parent. So if I tell you the parent of a discrete state, I can tell you everything about the transition probabilities of the parent state. And then if these are hidden, I assume that each one of these states can generate observations, potentially noisy. And then a hidden Markov model is basically going to be, a hidden Markov model is composed of a Markov chain and an observation model that satisfies this property, which tells you observation variable from a state, if given the true state of the system, you can fully characterize the distribution of the observations that can generate. Right? So this is usually people don't mention that directly when they're talking about POM-DPs or MDPs, but basically what an MDP is trying to control a Markov chain, a POM-DP is trying to control an HMM, and it's nothing more than that. All right? And then this is going to help us, so keep that in mind, because now we're going to go through a few equations, and then you're going to be like, oh my god, it's so hard. It's not. It's actually very reasonable, and you're going to go through a lot of it. So just to show you again that these things are relevant, this is actually based on a question from my qualifier exam in RAO. So basically here we have R2D2, and it's moving around the grid. And then so basically the model that I'm using here is whenever you tell R2D2 to move in some direction, it moves with high probability, and sometimes it gets stuck. So here what you see, so this is the true state of the system, the true state of R2D2, which I cannot observe. And here in this beautiful heat map or something, what I'm trying to represent is the distribution of problems. So that's the belief state. Whenever I talk about belief state, basically you have this in your head. which is just a distribution of particles of like possible locations where the robot could be. So as you can see, as the robot moves, the belief state kind of like moves along with it. And whenever it's close to one of these beacons, and then these basically measure the radial distance from them. Whenever it approaches one of these beacons and gets a measurement, you can see that the belief state gets reduced. Because basically we can use a sensor update to improve our knowledge of where the robot is. Right? So let me show you exactly how we do that. Because that's important to understand what RAO star is doing behind the scenes, because it's nothing more than that. So I'm assuming that everyone here probably has a basic understanding of probability, but in case someone doesn't, I'm going to give you a one-slide introduction to Bayes' rule, which is the core of belief state inference. So basically, let's A and B be two random variables. We can write their joint as the product of their conditional and marginal, but at the same time, I could have written this in the inverted order. I mean, I can just take the conditional B given A, and then since these two things are the same, I can say that these two things are the same, and then I arrive at B, right? And this is my favorite equation, because it basically allows you to go from, so basically usually what happens is you're trying to estimate the probability of the effect of the causes or the heat state given the observations by having a prior on your heat state, a model of how observations are generated by your heat state, and that's it. Well, and this is the partition effect, you know, indoor normalization effect. Right? So, I don't know, equations are usually, they are scary. So let me show you a few examples of how to do that, actually in that grid. So, in the notation throughout this lecture, whenever I write probability of an uppercase letter, this is a random variable. Therefore, this is a probability distribution of possible states at time t. So as the gentleman asked, let's suppose that we have b possible states. If this is a probability distribution of the possible values of s, what is this? Is this a vector? Is this a matrix? Is this a number? What should this be? So we have d possible states. S could have d possible values. And is a what?
Multinomial distribution.
Oh, no, I mean not necessarily. I mean, I'm not placing any constraints on the form. I'm just asking the data structure. So if this is telling you a probability distribution over all possible values of s, and I have d possible values, what should this be? A vector. Who's that vector? Perfect. A vector of how many entries? Exactly. All right. So every time you see this is not a number. This is just a vector that for every possible value of this variable at a time is going to give you a number. And this is just to introduce the next term. So whenever I write the random variable equals to a value, which I can also write as a lowercase letter, I'm basically saying what is the probability according to this distribution of the true state being S. In this case, what is this? Is this a matrix? Is this a number? Is this a vector? A number. Perfect. With what type of property?
Less than 1.
Exactly. It is a probability value, so it's a number between 0 and 1, because we're dealing with discrete states. All right. Cool. So, for the sake of running RAO star, or basically any of these probabilistic planning algorithms, what is important for you to know is how to perform filtering. And in the HMM jargon, you can also call that the forward algorithm. Right? So basically the problem is, assume that you have a set of observations up to this point. What is the probability distribution, so this is a vector, of my current state? Right? And now, along with all of you, with active participation, I would like to derive the simple algorithm that allows you to perform filtering. So let's start with that. And I'm going to bootstrap the discussion by telling you that it's probably useful for us to take the last measurement and split it from the previous ones. Okay, so I'm trying to compute this in a nice way, a way that I can go there and implement on my computer and see exactly what you saw in that animation with the RGHG. So, what should be the next step?
Can you use some conditional independence properties?
Yes, this is going to be in 2 steps.
Okay.
But before that, so can someone suggest So remember that we were operating with HMMs, and I just told you about this one probabilistic rule that is very interesting. So what do you think we should use? Just say it.
Bayes rule.
Perfect. All right, Bayes rule. I mean, if you get, the more you participate, the faster we go, and I can actually answer your questions. So let's use Bayes rule. So basically what we used Bayes rule for was to take this observation and to flip it with the current state, and of course we have to multiply this by the margin. So, looking at this, all right, so Bayes. Now the gentleman in front, when you mentioned conditional independence. So where can we use conditional independence here? And remember that we are talking about an HMM.
Because if you're given X, and then your probability of O only depends on X, not anything before that.
Perfect. Exactly. So all of this horrible thing here disappears because if it's an HMM, we're assuming that if we know the current state, this probability distribution is completely specified. And we actually have this number. So nice. Now we have this nasty thing. All right. So how can we get rid of this nasty thing? So the probability distribution of the current state given all the observations prior to the current one. This is a little bit harder, but what would you suggest that we do? Remember that an HMM has an underlying Markov chain.
Maybe you can use the Wrapup algorithm to calculate the most probable state based on the previous observations.
Yeah, this is very advanced. It's actually, so, but it's actually not the answer. In this case, so the Wrapup allows you to maximize paths in your discrete state, but here I'm actually trying to compute this distribution exactly. So, what do you guys suggest? Nothing? All right, cool. So let me suggest it for you. So since we're working with a Markov chain, it would be really, really helpful if we knew the previous state, right? Because in a Markov chain, if you know the previous state, the probability distribution for the current one is completely specified. So why don't we just do that? So basically here, I'm marginalizing over the previous state. And that's just from basic problems. So basically, I added st minus 1 here, and then I wrote the join as the conditional times the margin. Now, conditional independence again. What can I use conditional independence for to simplify the equation? Where can I use it? Come on, guys. Last lecture. So, how can I simplify this equation?
Your observations in your first probability don't matter. Your state is transition zone depending on the previous state.
Very good. Very good. Exactly. Because the underlying model that we have for an HMM is a Markov chain, if I know the previous state, I definitely know this distribution. So this is fully specified. And now we're left with this. But what is this?
Oh, you can use the dynamic programming to keep expanding that.
Exactly. So I mean, you don't need necessarily to use dynamic programming, but it is true that it's a recursion. This is this one step into the past. And then basically what you can do is you can keep so basically if you can compute now as a function of the previous step, you can do that over and over and over so as to compute this number. Or if you're computing things forward, you start with the initial belief and then you do one step filtering and then you do two-step filtering, three-step filtering, and so on. So right now we have derived one of the big parts of RAO or any probabilistic planning algorithm that deals with belief states, which is how to perform filtering. So first, you start with an initial distribution, so you have a probability distribution of your previous state. You use your transition model, which is stochastic according to your HMM, and then you call this step prediction. Once you have your predicted belief state, which is also a probability distribution, you update it using Bayes rule to get your unnormalized updated belief state. And the last step is just to normalize it, to compute that partition function, that normalization factor that makes all your probabilities central. And that's it. So when whenever you're RAO or any probabilistic planning algorithm that deals with hidden state, what it's basically doing behind the scenes is this. It's trying to use all the information that it can to compute its belief about the current state of the system, because that thing is hidden for it. If you had an MDP, this would not be a problem because there is no uncertainty about the true state of the system. You just look at it and it's right there. For hidden Markov models, or any probabilistic planning algorithm with belief states, the only thing that you can have is a belief, right? Cool. So let's try to do, this is just to show you some numbers of how we can do that in that scenario. I'll show you. So in the prediction here, let's try to compute the probability of being in this state. So we have this belief state and we say, let's move right. So the question is, what is the probability of the system landing at the red square after I tell it to go right? So what are the possibilities here? Well, perfect. It could be anywhere, but I have a whole bunch of zeros, and these probabilities here sum to 1. So basically my belief state is telling you, well, I don't know where I am, but I think I am in one of these 4 states.
But you don't know the probability on the move right. Maybe it jumps up 2, maybe it goes left 2. Maybe you haven't told us the...
Oh, but these sum to 1. So because belief states have to sum to 1, you know that all the other probabilities are 0.
For the current state, but if you told it to move right, you haven't told us the probabilities on SFT minus 1 to SFT. Oh, no.
Perfect. All right. So here what I'm telling you is, if I tell you to move in some direction, you will move with high probability or state play.
So the 1 chances are the ones you've shown and the 2 that are right.
Exactly. So if I want to write here, there are 4 possibilities. Either I was here and I moved right, or I was here and I stayed here, or I was here and well, I moved right, which is not possible, or I was here and I moved up, which is not possible. But you can just write this statement with these numbers. You know, you just use the equations that we have just seen. And let's go very quickly through these. What is this number? What is the probability of going from green to red if I tell you to move right?
0.9?
90%. Perfect. What is the probability of being green?
0.6.
What is the probability of going from blue to red if I told you to move right?
0.
0. Perfect. What is the probability of being blue? Perfect. So basically probability, or equations usually look hard, but if you actually look at what you're doing, it's a very common sense type of thing. So you're basically just combining the probability of being in a state times the probability of transitioning to the next state. Then you're going to get these numbers when you're going through the slides on your own, and you're going to get this 0.56. Right? So now for the sensor update. So now we did prediction. Let's do the sensor update step. And now this was me trying to adapt my pulse question to a grid. So basically now I have a simple beacon. So this beacon works as follows. It can give you a measurement of radius, so it can tell you how far you are in kind of like this squared circle sense. So kind of like 0, 1, 2, 3. So it can tell you how far you are or return nothing. All right? And then the question is, if your robot is moving around, how can you incorporate these measurements into its belief state? Right? So let's try one example together. And then the procedure is going to be, we're going to try to compute for each one of the possible states the posterior distribution, and for that we're going to use Bayes rule, just like we have just. So we have this number, which was the prediction step that we just went through, and now we're going to use the likelihood of each one of the measurements to compute the updated probabilities. Right? All right. So I went there, I took those probabilities, and I used the prediction model to compute this new belief state. All right? You should go home and check it, that this is perfect. I hope it is. So not only I told the system to move right, but now this beacon here told me, by the way, I sense that you are 2 squares away. 2 squares away in kind of like it. So this is 1, this is 2. So it's saying that like you are somewhere around here.
So how do you still have probability at 1 square away then, because your model says it's either going to return 2 or nothing if you're 2 squares away.
Perfect. Yeah, yes.
Oh, you have it.
We're going to arrive at this conclusion. All right.
It seems unrealistic though, like that you would have sensors that either give you the correct answer or no answer.
Well, it is. You could say something. For example, you could have a model that gives you the right measurement with high probability and then a wrong measurement with low probability. This one, you can say that there is some post-processing of your sensor that if it has high certainty that you are at some distance, it will output. Otherwise, it will output nothing. So it really depends on what you consider to be your sensor. I'm not saying that this is the best way to model it. It's just one way that it actually fits its slide. So let's try to compute the posterior distribution of being in this state. So Now, we're basically going to take the predicted probability and we're going to multiply by the likelihood. What is this number according to this model? I think I heard it. 0.8, exactly. And then basically for each one of these possible, for each particle on my belief state, for each one of these possible squares, I'm going to multiply it by the likelihood of that state generating the measurement 2. So let's try to do it together. What do we multiply this square by? This one. This one. This one. This one. This one. Awesome. See? You know exactly how to do new state updates. So are we done? No. What is missing?
Normalize.
Perfect. Exactly. Because we have to still compute the normalization factor. So after we normalize it, ta-da! So that's basically telling you that I started with that belief state here. I told the robot to move right. It gave me this kind of like smeared belief, which is larger. And then I used a measurement from one of my beacons to now update. And now I know that the robot, instead of being one of these 4 squares, it started with this square being the most likely, and now this one is the most likely with this L being all the other possible sites. Right? I mean, RAO star, not only RAO star, but probabilistic planners in general, basically do that over and over. Particle filters do that over and over. It's not a hard thing. Just if you look at the equations, it looks daunting, but it's not. It is computationally intensive, especially if instead of having 4 particles, you have like 1,000. But it's not hard to understand what's going on. Right? So we're done with all the background that we needed to understand what RAO star does. So let's talk about RAO star, which actually I'm going to leverage your prior knowledge from the excellent lecture that we had from the group that presented the probabilistic plane, AO star and LAO star a few weeks ago. So before I tell you what RAO star does, and RAO star is a really simple thing. I just wanted to give you like a high level intuition. So basically RAO star is a combination of AO star with belief states that you all know how to handle right now, and execution risk that you have no idea what it is, but I'm going to tell you. That's why I'm here. So basically, from AO star, please refer to our previous excellent lecture that talked about AO star, how do you do planning on an indoor graph, how do you search using heuristics. So RAO star is basically going to do the same thing. So the 2 key properties of RAO star are 1, just like AO star, it uses an admissible heuristic estimate of the value of the policy to be able to explore promising policy, not values, but kind of like promising policy choices first. So if you are trying to go from here to there, you are probably going to start looking for policies that kind of like go straight as opposed to going around it. Right? And then the second key feature of RAO star is not only it deals with value, but it also keeps a heuristic estimate of the execution risk in order to be able to prune or detect that a policy is not going to meet your risk constraint. And by risk constraint, I'm basically referring to this. You define a set of constraints that your policy has to meet. Let's say, for example, do not collide with an obstacle when you're moving around. And then you say the probability of violating those constraints, in this case, colliding with the obstacle, has to be less than some value. And you're going to see that basically we're going to impose this intuitive English notion of safety using this thing called the execution risk, which I'm going to explain very thoroughly during the lecture. And then the way we're going to do this is by, just like AO star, we're going to leverage heuristic forward search from an initial belief state towards either a goal belief state or some performance maximizing path along the policy space. Right? So the input to RAO star is this thing called the chance constrained POMDK, which is a very complicated name for something that is not that hard. So remember from the AO star lecture that we were basically looking at MDPs. So an MDP is composed of a discrete set of states, discrete set of actions, a transition function, and a reward function. Here, if you go from the MDP to the POMDP, you add now a set of observations because your state is no longer directly observable, so these are the possible measurements that a sensor can generate. You add an observation function that basically tells you how noisy your sensors are at each one of the states. And that's fine, so that gives you the POMDP. And the CC part, which is chance constraint, is basically composed of these two things. It's a set of constraints that your policy must meet. And an example here, for example, when you're trying to drive this robot around is, for example, do not collide. You can represent this mathematically as like, the position cannot be within any one of these obstacles, but in English you can understand this, do not collide. And the risk bound is basically saying, well, if my risk bound is 1%, I'm saying that I will not accept policies that have a collision probability that is more than 1%. But if it's less than that, I'm willing to take it. And then the question is, why would I be willing to take a policy that has a risk? Right? Should we always go for a policy that has no risk at all? Yes or no? Perfect. So it is a function of how much your system costs, if you're thinking in terms of money. But what do you think? So should we always try to minimize risk as opposed to bound it? What do you guys think?
Bounding.
Why do you think bounding is better than
If you're
minimizing?
trying to minimize, for instance, reduce the risk to zero, your system can choose something, unbelievably bigger that makes and realistic moves. Let's say the object is here and you're moving over there.
Exactly. So basically, if you're trying to operate in the real world, let's say, for example, you're trying to plan a trip to like California. If you want to go there and you are afraid of like dying of an accident, you kind of like have a non-zero probability that if you take an airplane, that airplane might crash. And if it crashes, the probability of you dying is very high. However, you still take the airplane. So in this case, the risk minimizing policy would be do not travel at all, because that will actually bring your risk to zero. The problem with risk minimizing policies is basically you end up being too conservative. So the reason why we have this whole contraption here with risk is basically to tell you sometimes when you're playing in the real world, risk is something that you cannot avoid, and sometimes if you try to minimize, you end up being too conservative. So let's try to acknowledge that that's a reality, and then we're going to make sure that we are safe by having these chance constraints, these bounds on the probability of violating constraints, and within those bounds, let's try to optimize performance. So this is the whole idea behind what a CC bound.
That's a big modeling question. So in this case, why don't you put a risk in another objective function and then you solve like a pre-compensations and you choose one from the curve instead of
Perfect. So this is, I get this question every time you present. So you have the people who solve POMDPs using, for example, a purely cost-based approach. And then they say, well, if you violate a constraint, just put it as a penalty in your objective function and you're all set. So this is actually not true. So you can do that, but the thing is, it's actually there is a paper in 2010 by Undurci and John Howe from MIT. He's showing that actually you can find there is a non-smooth mapping from costs to risks. So actually having this cost-based approach to risk can lead your system from being, by just changing the value of the cost continuously, you can go from a completely risk-taking agent which behaves inappropriately because it's too risky, to a completely risk-averse agent that does basically nothing by just changing your costs smoothly. So it is not the case that risks and probabilities are equivalent to costs in all situations. We can talk about, this is a very involved discussion, but the bottom line is it's not necessarily equivalent. All right, so just like AO star, we're going to search from an initial belief forward and let this big red blob be the set of all possible belief states that you could encounter in your application. So if I'm searching from an initial belief state, in terms of pictures, where do you think my search space is how do you think my search space relates to this red blob? It's going to be bigger, smaller, it's going to be outside, kind of a little bit inside, a little bit outside. Where is my search space going to be contained?
That's where you think you are?
These are all possible belief states for my system. So my search space is going to be where? A subset. Perfect. All right. So if you're searching from an initial belief state, the set of reachable beliefs from your initial belief state is certainly going to be contained within every possible belief state, right? Now think in terms of the solution. So now I'm trying to find the optimal solution that goes from the initial belief to some goal belief or some, basically tries to optimize performance. Where do you think this policy is going to be contained? It's going to be contained here, kind of here, a little bit here, outside. Where do you think it's going to be? Subset of the region. Perfect. Exactly. And now we have heuristic forward search from the initial belief state. Where do you think, so AO star or RAO star in this case, where do you think is the space that RAO star or AO star for that matter explores? Is it going to be here, here, overlapping here? How do you think it's going to look like? Blue, inside the blue? Can you have a search space that is smaller than the solution space? No. So it's probably bigger. But how much bigger? Can it be bigger than orange?
This is not reachable.
Exactly. It's basically going to be here. So the space that heuristic forward search is going to explore is definitely cannot be smaller than the solution space, but it also cannot be bigger than the reachable space. If you have a very good heuristic, something that actually tells you very precisely where to go next, so that you basically, explore very little far away from the policy, the optimal policy. So how would green and blue relate to each other? If you have a very good heuristic.
They get close together, almost the same.
Excellent. You're a very good cheater. What if you have a very bad heuristic? What do you think is going to happen? A heuristic that basically tells you nothing. You say like, oh, I want to get you Boston, to like Fenway Park to see the Red Sox play. And they say, where should I go? And the heuristic says, I don't know. I have no idea. Or like, go to Somerville first. Or take a trip to California and then back.
We're going to orange.
Excellent. See, you all perfectly understand what I'm going to tell you. It's all very simple. So yes, that's exactly what heuristic forward search does. And that's why it's so important to find good heuristics. Because the better the heuristic, the less time you spend exploring things that you didn't really have to. Cool. So now transitioning to the RAO star specifics. RAO star, since it deals with hidden state and systems for which you cannot observe, you have noisy sensor measurements and you have uncertainty about the true state of the system. Every node on the search graph that I'm going to show you is going to represent a belief state. And this belief state is exactly what we have gone through during the first part of the lecture. So it's a set of particles. Each one of these particles represent a possible state that the system could be in. And then this height here is basically representing the probability of you being in that state, given your history of actions and observations. How do you compute those? Filtering, which you all know how to do already. And then another thing about RAO star is within each one of these states, remember that we have constraints. So for each one of those states, we have a distinction between states that are safe and states that are unsafe. And here, unsafe states are painted in red. A state is going to be said to be safe if itself and the path that led to that state do not violate constraints. So for example, you're going to say the state in your path planning problem, if you must use that for path planning, is going to be a state that had no parent colliding with obstacles along the way. Right? So that's it. Every time you see a node in RAO star, it's going to boil down to a belief state. So this is basically extending the RAO star framework to partial observability. So now your node has a belief state, and then it is the same and/or graph that we had before. So an OR node represents agent actions, and an AND node represents noisy sensor observations. So down here, what are these nodes down here? What do they contain? Do they contain states, probabilities, probability
Next purple state.
distributions? Exactly. It contains belief states. So you go from belief states to belief states. And what are the annotations? So this is an AND node. Remember from the AO star lectures that these were annotated with the stochastic transition probabilities? So what do you think it's going to annotate the edges now? It has something to do with partial observability. So what did we add when we started talking about partial observability? Exactly. You guys know the answer, you just have to say it. So, yes, exactly. So these edges are going to be annotated by the probability of observing each one of the possible observables at this belief state. And then you're going to say, oh my god, but I don't know how to compute it. But I'm going to tell you how to do it. Right. So basically, now we're going to take this and or graph, and we're going to squash it into one hypergraph representation. So instead of having two types of nodes, now what we're going to have is only OR nodes. But the thing is, every time you take an action, instead of having a single child as the outcome, we're going to actually have a family of possible children. All right? And we're going to call this a hyperedge. And therefore, this becomes a hypergraph. It's just a handy way of representing the data structure. Right? And then for each one of these hyperedges, they're annotated with the probability of making these observations, which is the next thing that we're going to talk about. Okay? All clear?
So in yours, the probability of actions always had, or sorry, your observables always had some zero. So, you know, there weren't errors. If you have observables that can give you errors, it seems like your graph would just explode to infinity. You know, so you always have some sort of tolerance you give to that, where now you just set that at zero probability.
So when you say measurement errors, you're basically saying that your sensors are more noisy. I mean, the more noisy your sensors are, it doesn't really.
Well, you filtered your sensor noise to say, okay, if I'm 2 squares away, I'll get 2 to 80%, and I won't get anything if I'm not.
Exactly. So the important thing here is not necessarily the level of noise. You could have a sensor that basically gives you no information. It could give you true or false with 50% probability. So that doesn't really affect your.
Well, I mean, because DK now has gone to however many nodes that is.
Exactly.
All the other ones you had beliefs about have those nodes, and those will keep filtering through.
Perfect. So what really affects you when you have a sensor is the cardinality of your measurement space. So basically, if a sensor can generate 1,000 possible measurements at a state, this thing here is going to be huge. Or if you have a belief state that can generate 1,000 possible observations, this is going to be huge. The level of noise, I mean, if you compute the entropy of that thing, it doesn't really matter. Because the entropy is going to be measured here in the hyperedges. So that's going to affect your filtering problem here. Basically, if you have very entropic sensors, if you have sensors that give you very little information, basically what's going to happen is this belief state is not going to be very different from this belief state. Because your sensors didn't help you.
There's still got to be some probability. I mean, if your sensor, you know, gives you, okay, 80% it'll give you a 2, you know, 15% it gives you a 1, even though you're 2 away, 5% it gives you a 3, even though you're 2 away. So there's a lot of options. If that were to carry through, so you could never cull out some of your tree, then you would have like probabilities of, you know, 1 times 10 to the -5 hanging out in your tree that you're still carrying forward.
So this is a great. So yes, if you have very low probabilities on your tree, they're going to be there and they're going to annoy you because you're going to have to compute that branch, but it's going to have very little impact on your search. This is exactly relates to Professor Rim's initial comment of like, can you actually limit your search to the most likely outcomes?
Yes. Yeah, so is there a technique to just say once the probability gets below something, we cut that off?
Exactly. So I'm not going to talk about it today, but basically with RAO-SAR, what you can do is whenever you have these probabilities, you can have an overestimate of the risk, which means if I ignore this branch, am I still guaranteed to meet my risk bound? And you can basically prune that whole thing and then remove all those computations while still giving you a guarantee of safety. You do lose optimality when you make this pruning, but it is possible and it saves you a lot of computation. So it's a great point. It is very relevant. I'm not going to talk about it right now because it just complicates the process, right? So here, basically what I'm going to talk about is how can you generate a full set of observations that you can compute these problems, right?
See, that's pretty much the section we had on Monday. So for instance, you know, there's some low probability state. How can you print it out? Actually, you print it out by allocated rates. You're willing to tolerate.
Sort of. I mean, you're going to see, so here we have a different measure of risk. It doesn't do the risk allocation in the sense that we have seen before. It does like a dynamic risk allocation. But you could see as some sort of like version of that. Exactly. So you basically, the risk allocation, we're going to say RAO-SAR propagates a risk allocation down the graph. And as long as you are within that risk allocation, if you want to call it that, you're fine. So yes, this is a perfect point. It is related. So basically this lecture relates to a whole bunch of material that you have seen before. That's why it's the last lecture. Right. So let's now try to compute these probabilities because I haven't told you how to do it. So the rest of the lecture is just going to be, you know, to understand RAO-SAR, we have to know how to compute the transition probabilities. We have to understand how to compute estimates. We have to understand how to compute execution risks, and then how to put them all together. And these we're going to go through very quickly. It's not actually hard, and we're going to have lots of examples. So let's start by computing those probabilities that label the edges, right? So basically, if you have a belief state and you take an action, and you have these probabilities, the probability of observing, let's say, observation number 1, given that you took that action and you had a previous belief state. And here you have the posterior belief states that you get by performing what operation? So if you are in this belief state and you get observation 1, how do you get this new belief state? Could you say that out loud?
Filtering.
Filtering, exactly, which you already know how to do. So filtering. So assume that we started with this belief state. And basically what we're trying to do is to compute this probability. So for given my belief state in the action that I just took, what is the distribution of possible observations that I can have? So basically you can compute that by, again, you try to marginalize over the current state because that would help you a lot with your observation model. This is known. And then what you're going to have is probability of sk plus 1 given akpk, but that's the prediction probability. Remember from filtering? So basically, to compute these transition probabilities, it's just using the things that we already know how to compute. You're going to compute the predicted belief state, and for each one of the possible observations, you're going to take the probability of being in that state, and you're going to accumulate every state that can generate it, and then the likelihood of generating that particular observation at that state. Looks.
So a question about the observation model. Do you actually use some clustering mechanism for doing observations?
Oh, no, this is part of the model. So this is part of the HMM model.
So it's hard-coded part?
Yes,
Okay,
exactly. This is model-based. We assume that these things are given.
Okay.
All right. Looks hard, right? But it's not, because now we're going to do an example. So assume that we have a state with two particles, a belief state. And then we take an action, and then we have, from this state, we have 4 equally likely transitions, and from this state, we have 2 equally likely transitions. So now we have our new predicted belief state. And now, let's suppose that we have this observation model. We say that at blue squares, so blue squares can generate two observations, O's and dashes, and green states can generate O's and crosses. Now the question is, what is the probability of generating O? Can you guys tell me? How would you go about computing that? So what is the probability of computing O in this situation? What is the probability of observing O from this belief state? Exactly. So what should I do with this belief state?
Just replace the OK plus 1 with O, and then use the probability of SK plus 1 in the SK class with the probability of O, and then time your belief.
Exactly. So for example, let's start with this state. What is, so this state has a, so these probabilities correspond to this term. So I have this probability of being in this state. What is the probability of generating O at this state? 0. So disappear. What about this one? 0.8. What about this one? What about this one? Ta-da! See? It is actually much easier than you would expect. If you look at the equation, it says, oh, it is so hard, but it's actually easy.
Why is it?
Yeah.
Why is it 0.51?
Oh, it's just because it came from this belief state that it had a probability P and 1 minus P. And then we have equally likely distribution, so you get the probability gets partitioned. In the end, if you add these probabilities,
So that last row should be 0.5 times P. That's probably
0.5 times.
Oh,
Yes. It is the case. Yeah. Good catch. Nice. Yes, it is P. Perfect. Yes. So I guess you guys really understood it. See, you caught an error. Perfect. Yes. All right. So now let's move on to the value estimates. The value estimates are very, very easy, and I'm going to relate it back to the AO start lecture. So remember in the AO start lecture, we had the value of executing an action at a state was given by the reward, the immediate reward of executing an action in that state, plus the average value of the optimal future reward and the transition probability to that next state. What is the problem with this equation?
There's no risk.
No. It's non-computable at time k. I mean, it is if you go regression. So that's the whole thing of dynamic. So when you mention dynamic programming, so basically in order to compute the value at k, I need to know the optimal value at k plus 1, and so on and so forth. So these equations require you to know the future. And that's why dynamic programming works from the goal back. So basically they use the Bellman backup equations to basically recursively compute these things, and once you know the optimal values at one layer, you can compute the optimal values at the previous one, and then the previous one. Dynamic programming is the most beautiful algorithm ever, right? So what we're trying to do here is in many cases, so for example, value iteration tries to do that. It requires iterations, because if you have loops in your belief state, your dynamic programming might not converge in one step. But sometimes, as you have seen in the AOSTAR lecture, the group pointed out, sometimes, computing dynamic programming or value iteration for your whole belief space can be intractable, because basically you're running that whole algorithm and it grows, it's polynomial in the size of your belief state, in your state space, but the size of your state space is exponential in the dimension. It's the curse of dimensionality, right? So the way they address that problem, they say like, well, I don't know that, but assume that I could estimate that. And for that, I'm going to use a heuristic function. And not only that, I'm going to assume a heuristic that is optimistic. Basically, it's admissible. So it's a heuristic that will never underestimate the value of being at a state. And if you have a heuristic that has this property, you can prove it's the same proof that you can use for A star to prove that it returns optimal paths. The algorithm will never prove the optimal solution. And when it returns the solution, it is the optimal one. But of course, we kind of want this to be easy to compute. Because if computing the heuristic is as hard as computing the problem, you gain nothing. Right? And then we go from this equation that is non-computable going forward to this equation that is computable going forward, because it only depends on quantities that are available at time k. So how do we extend that to belief states? What do you guys think is going to happen? It has something to do with probabilities. What do you think is going to happen with this equation? So now we have this, fully observable. How do you think this is going to be extended to the partial observable case?
Observation.
Exactly. So this t here, so this transition probability here, will be replaced by those observation probabilities that we just learned how to compute. What else? If you don't know your true state, how do you think that's going to affect your reward? If you just have a distribution of the possible states. Exactly. Basically, we're going to take all of these numbers and we're going to replace them by expectations. Perfect. So we're going to go from the fully observable case. So now, my reward became the expected reward. So these are the probabilities from your belief state times the reward of each one of them. So this is the expected reward. As the gentleman here said, this transition probability becomes the observation probability times this big H, which instead of being the heuristic of a state, becomes the average heuristic of the next state.
Could you decide to go for a more conservative planner by doing something like the best, guaranteeing some baseline performance instead of taking the expected value, for example, saying my reward is the worst possible one among them?
Exactly. I mean, so all of these things, so in this case, we're trying to come up with an algorithm that actually returns you the true optimal, but all of these things in most real-world planning problems, sometimes you don't really care about the optimal, and the difference between the near optimal and the optimal could be negligible, but the difference in computing those could be significant. So in many cases, such as what the gentleman here mentioned in terms of pruning very unlikely branches of a policy, these make complete sense in practice. People do that. In this case, we're not going to do it because we're trying to compute the optimal values, but this makes sense. For example, if you still want to be admissible or something like that, you could, for example, take the max, so taking the optimal value.
I have a good question about the justification of this use the expected value for the work here. What about the case that if my signal to noise ratio is small? So for instance, if my mean divided by my standard deviation is less than 1, do you think it's still reasonable to use this?
Yes. Yeah, it has nothing to, so again, it has nothing to do with the entropy of your belief state. So this thing, if you have a very entropic belief state, you're going to have a large distribution of probabilities across many states, but that does not affect the validity of using the expected value. What you can say is you could potentially be, since the system will have a true state, if you have a very entropic belief state, you can say, well, the expected value can be very, very far away from the actual true state of being that state. But in this case, I mean, this is basically as well as you can do, because the only thing that you have information about is belief state.
Well, don't you also have a problem that you could have a feasible problem that the algorithm won't solve? If you're constrained on risk, if you have very entropic sensors, your system could say, I can't plan this.
Yes. Yes. It is definitely the existence of a
I mean,
solution.
that's your trade-off for saying risk is a constraint rather than a cost function, right? I mean, if you do risk as a cost function and there's a feasible space, the algorithm would proceed and just do its best.
Yeah.
If you do risk as a straight-up constraint, you couldn't do that necessarily, right?
Exactly. So the question is whether bounding risk makes sense. If that's the case, well, so for example, if you just put risk as a cost and then you compute the policy, then the next question is what does the objective value actually tell you? The problem of using risks as costs is that the objective function basically loses its meaning.
Yeah, I'm just saying it's
So for
not
example,
black and
if
white, because if you could have problems here where, okay, I have a noisy sensor, now my robot's just going to sit there and say, well, can't do it with less than 0.1.
Which is actually a good thing, because what happens is if you have a very noisy, for example, if you have a very large uncertainty about your belief state, and you tell the system, I want you, for example, let's say the Woods Hole glider. If the Woods Hole glider starts with a lot of uncertainty about its current position, or a Mars rover starts with a lot of uncertainty about its current position, and is trying to drive around craters on Mars, instead of just the moment you use risk as a cost, you don't really know what the risk the agent is taking. So I mean, it will compute a policy, but God knows how much risk that policy is actually taking. With this framework, if you say something like, I want the probability of you falling into a crater being less than 0.1%, and if you give it too much uncertainty about the state, it will tell you, I cannot plan. I do not have enough information. You could, for example, wait for the next satellite to come by, give you an update on your current position, reduce your belief state, and in that situation, continue planning. So this is actually a good feature. So if you actually want to trust these systems and you want to make sure that they abide to your risk bounds, it's not really reasonable for you to just throw into the objective function and say, do as well as you can and we trust you. And if we actually want to trust that these things are going to be doing the right thing, having a numerical guarantee and actually having an agent that will say, I will not do this because I do not have enough information about my belief state, is a positive thing. So it's not really a flaw, it's more like a feature. Right. All right. So now the fun part, the execution risk. So basically, execution risk is a very intuitive thing to understand. Basically, we're going to say that the execution risk of a belief state is the probability of violating constraints. For example, when I say constraints here, we think about colliding at time k. So the execution risk at time k, you can think of as the risk to go. So I can violate constraints now, or I can violate constraints the next time step, or the next time step, or the next time step, until I go. So this is going to be done in a finite horizon version. Of course, so this is easy to understand. And basically this variable here is telling you, this is a binary variable that tells you it's 1, which means it's safe if the agent hasn't violated constraints in C until the ith step, right? So this is easy to understand, but it's nasty to handle. So you can take this and you can play around with the probabilities, and you end up with this recursion, which looks a lot like the utility recursion, but it is different in fundamental ways. I'm probably not going to have time to go through these specifics, but if you are interested, you can punch it. But basically what I'm saying is, we can compute execution risk, which is basically the risk to go for the agent using this recursion. And now we're going to learn how to do it, and you're going to see. All right. So the execution risk is composed. So the two important things is, first is, what is this R term? R measures the immediate risk of the current belief state being in violation of constraints. And it is defined as this function. So it's basically the probability of being, so according to the belief B, is the probability of being in state K times this constraint violation function, which in the simplest case is a binary indicator, which is going to be 1 if the sequence of states, the path, leading to the state SK violates constraints. That's it. It is an expected value. So it is a probability because it's the expected value of an indicator function. All right? So the other term is this observation probability here that has this SA, which stands for safe, which looks a lot like the observation distribution that we just learned how to compute. It just has this additional conditioning here. It conditions the fact, so it computes the probability of observing OK at time O at time k plus 1, given AK and BK, but it requires you to be at a safe state time k. So that, it's going to have the exact same form as we had before, but now we're going to have safe predicted belief space. And how do we compute the safe predicted belief space? Very easy. It is the same thing as before. We're just going to take, when we're taking our transition model from our belief space, we're only keeping the particles whose paths do not violate constraints, and we are dividing by the marginal, which is the probability of being safe in the previous belief state, which is just 1 minus this term. Looks horrible, right? But it's not. It's actually very intuitive if you do it with numbers. So let's do it with numbers. Cool. So now we have this belief state here. Now I'm saying that this particle here is in violation of constraints. Let's say it means that the paths leading to it collide. I take an action. Oh, before that, otherwise I'm going to need the answer. So when I take an action in a propagated belief state, can a particle coming from this state not be read? No, exactly. Because every path stemming from this state here is in violated constraints in the past. So all of the children of this node will be read. And this one, let's say if you take a stochastic transition, you could, for example, land at safe states with this probability, or for some reason end up in an unsafe state, just so it's colliding with a wall because you didn't have enough certainty about your position. In this case, what do you think it's our term for this belief state? What is the immediate risk of violating constraints at this state? P. Perfect. All right. So now we know how to compute this.
Wait, why is that being packed?
Oh, because it's this one.
Oh.
So the risk is P. So let's now try to compute. Let's now try to compute the probability of observing O. And for this particular case, let's assume that these states generate O with probability 1, just to simplify things. What are the particles? Remember that we have to condition on the fact that the system was at a safe state at the previous time step. So look at who generates O. Look at where they came from and tell me which particle should I take into account when I compute the probability of this safe probability of observation. First 3, only 2. It is right. So it is a restricted subset. It's actually these 3. Because even though these 4 states generate O, only these 3 satisfy the property that they are coming from a state that was previously safe. And the only reason why you have to do that is to prevent double counting of risk. So in this case, you're going to take these probabilities and you're going to divide by the probability of being safe in the previous time step, which is 1 minus 1. So what about that term? It's still a problem, right? Because it still depends on the future. So what we're going to do is exactly what we did for the utility. We're basically going to replace this by an optimistic estimate of the execution risk for the mission. In this case, an optimistic estimate is an underestimate of the true risk. So, good, admissible, and at the same time, it should be easy to compute. And then we can go from this equation that's not computable forward to this equation which is computable forward. Now, in 10 seconds, can you guys give me a good, not really good, but at least a non-trivial admissible estimate of this number, just by looking at this equation?
Zero?
So 0 is true, but it's trivial. What is a non-trivial one? Is a little bit further from 0.
The immediate risk is the next one.
Exactly. Perfect. So if you just say that the execution risk is always going to be equal to the immediate risk, this is guaranteed to be admissible. And this is very easy to compute. because this is the expected value of the risk function over the current belief state. Perfect. Right. And then another cool thing about RAO star that actually allows you to prune risky, remember like the it's a trap? It allows you to prune risky branches early is using, this nasty equation is basically coming from this one. So it's just a rearrangement of these terms. And if you look at this equation, you're like, oh my God, why does it look so hideous? Basically what this equation is allowing you to do is assume that your parent has a risk allocation and has an immediate risk. This equation allows you, for each one of the children, to compute a new risk allocation for that child as a function of the transition probability to that child, which we all know how to compute, and the risk terms for the parent, and the execution risk estimates for the siblings, which are these ones. And God bless PowerPoint for colors. So here you can actually see with colors where each one of these things. So basically this equation allows you to take a risk allocation for the parent and propagate it forward for the children, right? So it's not done, so it's not the constant sum execution risk that you have seen, for example, in IRA or CRA, but it is an analogous thing, right? So, and just to show you a risk example, let's say that R2D2 is in the square. I tell you to move forward. You can either achieve this cleanly or bounce off the wall, and we're trying to compute the probability of bouncing off the wall and actually having a collision. So if I tell you to move down, and we start with full certainty about your belief state, what do you think the next belief state is going to look like?
90% will be safe.
Perfect, exactly. So if I take this action, I'm going to actually have a belief state with two particles. They all share the same position because they all achieve this point. But with 10% probability, if I don't know where R2D2 are, whether you collided or not, I'm going to have a 10% chance of having collided and a 90% chance of not having collided. What if I do that again? So can any transition to this from this state be in a non-collision? Be in non-collision? No. Exactly. So if you only do prediction, your risk can only grow, which is awesome, and we can talk about it later, but I'm not going to talk about it. So if you take this other action, what's the belief state going to look like in the next step? Sorry? Perfect. Yes, exactly. So now, as you said, the risk, if you keep going down this hall, and at every point you could collide against the wall, unless you have some way of measuring whether you collide or not, you have some sensor, your risk will only grow. And that's the importance of actually having sensor information in order to be able to compute these policies. Basically, if you told RAO star to go down this hall with no sensor information, it would actually be very scared, because it would say like, well, if at every point, every action that I take, I have some probability of failure, and this is very, very long, I'm afraid of going down, unless you give me some way of measuring whether I'm healthy or not. Which makes sense. All right. So in my final minutes, I just want to show you how to put this all together. It's going to look exactly like AO star with just the whole propagation of risks. So now the input is kind of the same thing as AO star, but with the red things being the additions that RAO star does. So a belief state, an observation function, and space and a function constraints. The output is exactly the same as AO star, which is an acyclic hypergraph. But the difference is, instead of mapping states to actions, it's going to map belief states to actions. And it is optimal, at least in this formulation that we just shown you. And the strategy is just like AO star. You're going to build your policy forward and use heuristics to estimate both the risk and the value of each one of your belief states. That's it. This is the pseudocode. It is basically the same as the AO star pseudocode. In red are what we add to add the risk capabilities, but it's basically the same thing. So instead of going through the pseudocode, let's go through the cute graphics that took me forever to put together. So, all right, so this is basically going to be, this is the hypergraph that represents the search key or the search graph. Highlighted is our best estimate of the optimal policy, and then whenever a node violates constraints, I'm going to paint it red. And for the sake of simplifying the graphics, now we're going to do the fully observable case. We have like every time a single state. But if you go to the belief state, you guys know how to compute each and every one of the steps. You know how to compute the transition probabilities, you know how to compute the estimates, the value estimates, and you know how to compute the execution risk. Every term. So now you're, experts. RAO stuff. So let's start. We start with an initial risk allocation of 5%. You say like violating constraints, whatever those constraints are, can happen in no more than 5% of the ones. Yeah. So we start with this initial belief state. In this case, is a single state, and then let's run RAO start and see how it works. So the first step is expansion. So choose an open node. What open node do we have to choose? I heard something say something.
S0.
Perfect. Choose S0 because it's the only thing that you can expand. So you expand it by basically taking the operators that you could. These are the probabilities, and these are just like cooked up numbers or whatever they represent. So here we're trying to minimize costs, so the rewards are going to be negative values. And then what we're going to choose, we're going to try to maximize this negative reward and minimize the cost. So we choose a node, we expand the operators. Now we're going to estimate the values to go and the risk to go at the leaf nodes that we just expanded. And we're going to say for these ones, because I didn't paint them red, it's going to be 0 risk, for each one of these leaves. And now I'm going to propagate the risk bounds. You're going to be like, oh my god, where did you get these numbers from? I got from this nasty equation. And I didn't add the equation here because I'm a nice guy. It's basically because it was taking me so long to go back and see what the equation was that I just added here. So it makes it very easy to understand where these numbers are coming from. So this number was produced by replacing these numbers. Right? So now I have this new risk allocation for those nodes. Now I can back up the values as we do with RAO start. So now I only have one node that I expand. If I choose A1, I have this expected value. If I choose A2, I have this expected value. Which one should I choose? If I'm trying to maximize it. Sorry?
Minimize it.
Well, I'm trying to maximize the negative thing. So,
The second one.
first one. Because this is greater than this one. Well, it's a maximization problem. So, minus 11.3 is greater than minus 11.7. So, we choose this one. Right? And then the execution risk, just to show you, it is within the risk allocation. Now, update G. What is our best estimate of the policy now? What is the action that looks the best at S0? Perfect. So now, because of our risk is telling us that this branch here looks more promising, we're basically going to ignore this side for the time being, and hopefully we will find a solution down here and never have to explore this side of the policy space. However, it might be the case that we have to go back. Right? So now we have our best estimate of the policy, which is if you are at S0, choose A1. And let's do it again. Let's choose an open node. Which node do you guys want to expand? And I hope you choose. What options do we have to choose from?
Just the ones with minimum risk.
No, actually, so the two open nodes that we have for the policy are these ones. So they are leaf nodes on your policy. And then I just going to say that we're going to explore this one because I like it better. You could actually explore all of them at the same time. It doesn't affect the parameters. It just affects the slide real estate. So now I'm going to take this node here. I'm going to expand it. Notice that now I have a node that violates constraints. So I painted it right here. So when we now we can go estimate the value and the execution risk for each one of them. Here, because the immediate risk is 1, the heuristic for execution risk is also 1. And now let's propagate the risk bounds and see, given this risk allocation, how this risk allocation propagates to the children. All right, and this is how, for example, at least for these ones, this is how I got you these numbers. Is there anything weird with these numbers? There should be 2 things weird. You guys have to answer quickly, otherwise I'm not going to finish my slides within time.
Negative 317%.
Exactly, and which is basically what it's saying is, if you need to meet this risk allocation at the root, and you propagate it down the graph to these children. It says, if you choose this operator, the only hope that you have to meet this risk allocation at the very top is if you have a risk of minus 317% down this policy. And here, even though the risk is 1, so we are guaranteed to every extension of this thing will violate constraints, here the risk cannot be greater than 20.8%. So that's basically telling you that if I choose this operator, I'm guaranteed to violate my initial risk allocation. So then it's a trap. It's going to say like, no. This is way too risky. Even if it looks good, you know, if you have your rover and you're trying to go down those, you know, in between those craters, you might say, oh yeah, I'm going to take the shortest path and go in between them. But it's going to say like, well, dude, you're going to just fall and die. So not falling and dying. So we actually don't add this to the graph, and we just keep this one. And now let's do the backup. At this node, you have one action, so you don't really have other things to choose from. So you have to choose the one that you have. And then if you back up the value for the root node, now you can either go this way or this way. Which one would you choose? HE, right? This number is better. All right. And now you update the policy. So what should the updated policy look like from these choices of values? This is going to change something. You're going to say, well, now that I further expanded this side of the graph, this doesn't look as promising as it would before, and I'm going to try a little bit on the side, which is exactly what AO star does. So this does exactly what AO star does. It just adds a layer of risk propagation and risk checking. So that's it. You know exactly what you do with RAO star. And it terminates basically when RAO star, the same termination condition as AO star, which is you will terminate once all the leaf nodes on your policy are terminated. Right? So these are my extra slides, which I placed here just in case. And then the key takeaways, just to finish the lecture, is 1, I talked about RAO star. There is nothing special about RAO star. Execution risk should be generally applicable to probabilistic planning, and regardless of the algorithm. RAO star just happens to be the one that incorporates it first, but there are a whole bunch of other TOMDP solvers that you could just extend to have a notion of risk and have them perform just as well on different domains as RAO star. Second, this is related to our discussion that we had here, is risk-bounded planning. Whenever if you go out in the world and you're trying to do autonomy, risk-aware autonomy, trying to be risk-bounded tends to be much better than to try to be risk-minimal. Basically because risk-minimal policies tend to throw you all the way into the super conservative side of the force, right? And then the third one is, in order to be able to, I didn't tell you about it, but for example, that RSS, the demo with the music that I showed you before, it had to measure scheduling risk. In order to be able to run these planning algorithms quickly, as quickly as you saw running on the video, you need a very efficient constraint checker. And that's the reason why, for example, Andrew's lecture is so important, because if you cannot check for chance for risk-aware consistency quickly, these algorithms just take forever. Right? So with that, I'm done. Thank you very much.
Thank you very much for capping off the course with a great lecture, and Andrew as well on Monday. I really appreciate that. This is just a reminder to you that to fill out, either you'll receive a course 6 or 16 online survey. It's particularly important for us to get feedback from all of you, right? We've made a lot of changes in the course by the fact that we've had a large kind of growth in the course 6 population at the MEng level, right? So we've added a lot of problem sets, right? A lot of the things that we've done in the advanced lectures. So it's very important to get all your feedback on the things that you liked and the things that you didn't like, so we'll adapt along the way. So please, please, please fill out those surveys. I also want to thank you guys for contributing to all the lectures, since you guys assembled about a third of them, and you guys did a fabulous job on those lectures. We really appreciate that. That's why we've been videotaping them. A final thing is just that, I think Steve will probably try to get some additional questions from you on the advanced lectures, but just as a straw poll, so how many like giving giving the advanced lectures and you thought it was a worthwhile learning experience, and how many of you would rather not do something like that? So how many liked doing the advanced lectures? And how many would rather not do that? Just have us lecture to you. Okay, great. Thanks a lot.